On January 31st, 2008, on a clear winter morning in Albuquerque, New Mexico, a single 25 kilowatt machine sitting in the desert converted sunlight into grid-ready electricity at 31.25% efficiency. That number was measured at Sandia National Laboratories, a Department of Energy facility, not a manufacturer's marketing department. Every parasitic load was subtracted before the final calculation. The tracking motors, the control computers, the cooling pumps. Net energy delivered to the grid divided by solar energy hitting the mirrors. 31.25%. Verified, documented, and published. That record was set 16 years ago. It has never been broken. No solar technology deployed anywhere in the world since that morning has demonstrated higher net conversion efficiency from sunlight to grid-ready electricity. Not the premium monocrystalline panels on the most expensive residential installations. Not the utility-scale photovoltaic farms covering thousands of acres across the American Southwest. Not the concentrated solar power towers with their fields of tracking mirrors and molten salt storage. Nothing. The technology that set that record is called a dish Stirling system. Total dish Stirling power ever deployed worldwide is roughly 3 megawatts. Total photovoltaic solar deployed globally is over 2,260 gigawatts. That is a ratio of 750,000 to 1. The most efficient solar electricity generator ever tested accounts for a fraction of a percent of global solar deployment, while a less efficient technology has conquered the entire market. By the end of this script, you will understand exactly how dish Stirling achieves nearly double the efficiency of standard solar panels, why the companies that tried to bring it to market all went bankrupt, and what that story reveals about how energy markets actually work when efficiency and economics point in opposite directions. The Stirling engine at the heart of this technology was invented in 1816 by a Scottish minister named Robert Stirling, who was trying to solve a problem that had nothing to do with solar energy. Steam engines were transforming British industry and killing workers. Boiler explosions were common and catastrophic. Stirling designed an alternative, a closed-cycle engine where heat is applied from outside a sealed cylinder. No boiler, no explosive pressure vessel. His key innovation was what he called the economizer, now known as the regenerator, a component that recycles heat internally between the hot and cold sides of the engine and dramatically boosts its efficiency without requiring any additional fuel input. The physics of the Stirling cycle turned out to be remarkable. It can theoretically achieve Carnot efficiency, the absolute maximum thermodynamic limit for any heat engine operating between two temperature extremes. The formula is straightforward. Efficiency equals 1 minus the ratio of the cold temperature to the hot temperature, both measured in Kelvin. The hotter the hot side and the cooler the cold side, the higher the theoretical ceiling on conversion efficiency. For over a century after Stirling filed his patent, this remained an elegant engineering curiosity with limited practical application. Then, in the 1970s, the Department of Energy and NASA's Jet Propulsion Laboratory asked a question that changed the trajectory of the technology entirely. What if you used concentrated sunlight as the heat source? A parabolic dish focuses all incoming parallel light rays to a single point at the focal center of the dish. Aim that dish at the sun, and you can concentrate solar radiation to more than 3,000 times its normal intensity. Place a Stirling engine receiver at that focal point, and the receiver temperature reaches 750 degrees Celsius. Against an ambient cold sink of 50 degrees Celsius, the theoretical maximum Carnot efficiency at those temperatures is 68.4%. Real Stirling engines with properly designed regenerators achieve over 75% of that theoretical limit in practice. The mathematics produce a net solar to electric efficiency that no photovoltaic technology operating on fundamentally different physics can approach. In February 1984, a prototype called the Advanco Vanguard achieved 29.4% net solar to electric efficiency at Rancho Mirage, California. It was the first world record for solar electricity conversion. The physics worked exactly as the thermodynamics predicted. The question then became why standard solar panels operate so far below this ceiling and whether that gap matters enough to change how solar technology develops. Standard silicon photovoltaic panels face a fundamental conversion ceiling that is built into the physics of the semiconductor process itself. At the cell level, the best commercial monocrystalline silicon converts between 20 and 22% of incoming sunlight to electricity. But cell efficiency is not system efficiency. By the time you account for inverter losses, wiring losses, module mismatch between panels in a string, and soiling, system-level AC efficiency in a real installation drops to between 15 and 19%. The gap between laboratory cell performance and actual grid-delivered output is structural. It cannot be engineered away within the photovoltaic approach. Heat makes the situation worse in precisely the locations where solar installations are most valuable. Photovoltaic panels carry a temperature coefficient of -0.3 to -0.5% per degree Celsius above the 25-degree standard test condition. In desert locations where solar irradiance is highest and utility-scale installations are concentrated, cell temperatures routinely reach 60 to 75 degrees Celsius on summer afternoons. That temperature rise translates to between 12 and 25% power loss compared to rated output, occurring in the exact conditions where the installation is supposed to be performing at its peak. The sunniest and hottest places on Earth are precisely where photovoltaic panels perform worst relative to their nameplate ratings. Fixed mounting compounds the problem further. Standard residential and commercial installations use fixed tilt racking oriented toward the south at an angle approximately equal to the site latitude. The sun moves across the sky in a continuous arc from morning to evening. The panels do not follow. Compared to dual-axis tracking systems that follow the sun through both its daily and seasonal movement, fixed tilt installations capture roughly 30 to 45% less energy over the course of a year. That is, energy arriving at the panel surface at suboptimal angles and being reflected away rather than converted. Every grid-tied photovoltaic system also requires a DC to AC inverter. That conversion costs another 3 to 5% of system output. But there is a subtler consequence of inverter-based generation that has become an increasing concern for electrical grid operators as solar penetration rises. Inverter-based systems provide no rotational inertia to the grid. Traditional power plants, whether coal, gas, nuclear, or hydro, all spin large generators whose physical mass resists changes in rotational speed and thereby stabilizes grid frequency during disturbances. As inverter-based solar and wind displace conventional generation, grid operators lose this stabilizing inertia, and frequency stability becomes an engineering challenge that requires additional infrastructure to address. These are not manufacturing defects or installation errors. They are physics limitations inherent to the photovoltaic approach that define the ceiling of what the technology can achieve, regardless of how well it is made or installed. The dish Stirling system was not designed as an incremental improvement on photovoltaics. It was designed on entirely different physics that addressed each of these limitations structurally rather than incrementally. The Stirling cycle benefits from larger temperature differentials rather than being degraded by heat. The same desert conditions that reduce photovoltaic output increase the temperature differential available to the Stirling engine and improve its theoretical efficiency ceiling. The Suncatcher, the most developed commercial dish Stirling design, operated consistently across ambient temperatures from -10 to +50 degrees Celsius. Arizona summer heat was an engineering advantage rather than a performance penalty. The dish geometry requires dual-axis tracking to function at all. A parabolic concentrator only focuses incoming light to a point when it is aimed directly at the source. This mandatory tracking requirement, which is an additional cost in photovoltaic installations, is simply intrinsic to how a dish Stirling system operates. The result is that every minute of sunlight arrives at the receiver at optimal concentration, with no cosine losses varying through the day. The system captures 30 to 45% more of the available solar resource than a fixed photovoltaic installation in the same location, simply because it has to track to function. The generator is a spinning shaft driven directly by the Stirling engine. No inverter, no DC to AC conversion. The Suncatcher produced sinusoidal three-phase AC power directly, grid-quality output at the point of generation. The spinning mass of the generator provides genuine rotational inertia to the electrical grid, the same stabilizing property that conventional power plants offer and that inverter-based solar cannot provide. At high renewable penetration levels, that physical inertia has measurable infrastructure value that grid operators are increasingly willing to pay for. On every technical metric that matters to solar electricity generation, the Dish-Stirling system is superior to photovoltaics. Efficiency, heat performance, tracking utilization, grid compatibility. The engineering validated the theory comprehensively. The Maricopa solar plant near Phoenix operated 60 Suncatcher dishes at the world's first commercial-scale Dish-Stirling installation from December 2009 through September 2011. Production data showed output 7% higher than engineering models predicted. During the summer of 2010, system availability reached 97 to 98%. For pre-production technology running in Arizona desert conditions, those numbers were genuinely impressive. Independent verification came from Europe through entirely separate research programs with no connection to the American commercial ventures. The Eurodish at the CNRS facility in France measured net solar-to-electric efficiency of 21.6%, peer-reviewed and published. The technology worked, and its performance was repeatable across continents and research institutions. And then the economics arrived. And everything that followed from that point is a study in what happens when superior physics meets a competitor whose price is falling faster than any market participant predicted was possible. That collision, the bankruptcies it produced, the supply chain collapse that followed, and what it means for whether this technology has any future at all, is what Part 2 examines in full detail. In 2008, the same year the Suncatcher set its world efficiency record in Albuquerque, photovoltaic modules sold for approximately $4 per watt. That price was already considered low by historical standards. The industry had been watching panel prices fall steadily for 3 decades and projecting continued decline. Nobody projected what actually happened next. By 2012, photovoltaic module prices had collapsed to 70 cents per watt. By 2020, they reached 20 cents. Today, modules sell for between 10 and 20 cents per watt. That is a 99.6% price decline from 1977 levels, driven primarily by Chinese manufacturing scale, state-owned bank financing, subsidized industrial land, and massive polysilicon production capacity that came online faster than any Western market analysis anticipated. The levelized cost of energy from utility-scale photovoltaics today sits between 3.8 and 7.8 cents per kilowatt-hour. The most optimistic academic modeling for Dish-Stirling at production scale puts it at 11 to 25 cents per kilowatt-hour. The best-case projection for the more efficient technology cannot compete with the worst-case reality of the less efficient one. Superior physics lost to sufficient physics that became extraordinarily cheap before the superior alternative could reach the manufacturing scale required to drive its own costs down. The financial wreckage was comprehensive and followed an identical pattern across every company that attempted commercialization. NTR, an Irish infrastructure firm, invested $100 million in Stirling Energy Systems in April 2008 for a controlling stake, essentially at the peak of Dish-Stirling optimism and the precise moment before the photovoltaic price collapse accelerated beyond any reasonable forecast. In 2005, utilities had signed contracts for 1,750 megawatts of Dish-Stirling capacity. The 850 megawatt Calico project and the 900 megawatt Imperial Valley project together represented the largest concentrated solar commitments in history at that point. Not 1 megawatt was ever built. Both contracts were terminated, and the sites were sold to developers who immediately converted them to photovoltaic installations. In September 2011, Stirling Energy Systems filed Chapter 7 bankruptcy, liquidation rather than reorganization, meaning the company was simply dissolved. Infinia Corporation, which had developed a free-piston Stirling design with potentially lower maintenance requirements, filed Chapter 11 in September 2013. Azelio, the Swedish company that acquired Cleanergy's dish Stirling technology, declared bankruptcy in July 2023. Every major dish Stirling company followed the same trajectory, separated by years, but identical in outcome. The manufacturing complexity gap between dish Stirling and photovoltaics was fundamental rather than incremental, and it explains why the cost reduction trajectory that rescued photovoltaics was never available to dish Stirling on any realistic timeline. The Suncatcher power conversion unit contained roughly 650 parts after Stirling Energy Systems spent years reducing complexity from an original 1,600 components. Add 82 mirror facets per dish, dual-axis tracking motors, structural framing, and cooling systems. A photovoltaic panel contains 0 moving parts. The manufacturing, logistics, and maintenance implications of that difference compound across millions of units and decades of operation in ways that no engineering refinement could bridge quickly enough. Maintenance requirements reflected that complexity directly. Hydrogen, the working gas sealed inside the Stirling engine, leaks slowly through microscopic gaps and seals and requires periodic replenishment. The receiver, operating at 750 degrees Celsius with daily thermal cycling from cold morning startup to hot midday operation, experienced heat pipe plugging, sodium corrosion, and fatigue cracking that required major attention every 5 to 10 years. Above 40 miles per hour wind speed, the entire dish must stow to prevent structural damage, meaning output drops to 0 during exactly the high wind events that often accompany weather fronts moving through desert regions. The supply chain collapse that followed the bankruptcies created a barrier that now exceeds the original manufacturing challenge. As of today, there are no commercial suppliers of precision parabolic mirrors sized for utility-scale dish Stirling. No suppliers of solar Stirling engines. No suppliers of dish-specific tracking systems. The National Renewable Energy Laboratory removed dish Stirling from their System Advisor model software in 2020, an official acknowledgement that the technology no longer warranted modeling support for project development purposes. The knowledge base is aging out of the workforce as the engineers who built and operated the Maricopa plant and the Sandia test facility retire without successors who have hands-on system experience. What remains is a verified efficiency record that still stands, a supply chain that no longer exists, and a competitor technology whose price makes the efficiency gap economically irrelevant for the foreseeable future. Dish Stirling is not a suppressed technology. It is not a victim of conspiracy or deliberate burial by entrenched interests. It is a tragedy of timing. The engineering worked. The physics was validated repeatedly across continents and research institutions. The efficiency record from January 2008 remains unbroken today. But efficiency is not the only variable that determines what gets built at scale. When a competitor's price falls 99% before you reach production scale, superior thermodynamics cannot compensate. The market chose good enough performance at impossibly low cost over optimal performance at uncompetitive prices, and the ratio of 3 megawatts to 2,260 gigawatts is the permanent numerical record of that choice. The most honest assessment of dish Stirling's future is narrow but not zero. Hybrid operation, combining solar concentration during daylight hours with biogas or natural gas combustion at night, increases annual energy production by 47 to 78%, according to University of Palermo research, and addresses the fundamental limitation of any solar-only system by making the heat source dispatchable rather than weather-dependent. In locations with expensive or unavailable grid power, direct normal irradiance above 2,500 kilowatt-hours per square meter per year, and access to biogas, the economics look different than they do competing against utility-scale photovoltaics on a levelized cost basis. That niche exists. The technology to fill it currently does not exist in commercially available form. What that leaves is a world efficiency record sitting in a Sandia National Laboratories dataset, a cautionary study in what timing and manufacturing economics can do to even the most compelling physics, and the open question of whether the next generation of solid-state thermal conversion technology learns the lesson in time. Thank you for watching this video. Click here to watch another video that might interest you.